Hi, I'm Lena Erickson, and this semester I have had the privilege of being the team lead for the Technology Commercialization project. This project is going to inform a national lab on the most high-impact research that is being done today. And that research has to do with a new chemical technology that didn't exist 2 years ago. This chemical technology uses a rare earth element that is not, in fact, so rare. But before you learn about this catalyst, I have some thank yous that I'd like to give. First, I would like to thank our mentors and inventors at Ames National Laboratory, Todd Dorkowski, Igor Slowing, Aaron Sadow, and Craig Forney. They have provided us with just a lot of mentorship and guidance, despite the fact that they're several states away. So to Todd, thank you. Thank you, and I hope you find this finds you well. Also, I would like to thank the CCEW staff. This has been quite a semester, and they have been through us the whole way. And their dedication to mentorship has, I cannot thank you enough for that. And finally, the people I would like to thank the most are the 4 people you are about to meet. These 4 people, Alexandra, Alex, Jack, and Stephanie. When I first met them, I had no idea how amazing they would make my semester. They are incredibly intellectually tenacious, and their analysis is going to have an incredible impact on the world from here and in their future careers. Not only have they been intelligent in making recommendations, but they are smart and funny and witty and rebellious. And I have enjoyed getting to know them so much. I've never been as proud as I am right now to welcome them to the stage. So welcome, Team Ames.
Technological innovation lies at the heart of economic growth, and U.S. national labs are key drivers of American innovation. Now, these labs were researched so that they could find scientific solutions to our nation's top problems. One of these problems is securing the domestic supply of rare earths, which are a set of critical materials that are necessary for national defense and for modern technologies. One of these rare earths, cerium, is underutilized and oversupplied, and it needs a new source of demand so that it can stabilize the current industry. In order to combat this, researchers at the Ames National Laboratory and the Critical Materials Institute have created a new cerium-based catalyst that could fit into the nylon intermediates production chain. However, the future success of a current lab-scale technology is far from guaranteed. So Ames contacted our team to navigate the massive, secretive nylon intermediates industry. In an interview with the commercial manager of an international catalyst supplier, our team learned that only 1 in 1,000 lab-scale catalysts actually make it into industrial use. And through our analysis, we have found that the Ames catalyst does not currently have commercial value. We are going to give Ames an actionable strategy so that they can fulfill their ultimate goal of finding a new use for cerium. And today, we're going to give you a glimpse into what it's actually like to have an impact on high-impact research at one of the nation's leading scientific institutions. Hi, I'm Alexandra Smith, a senior economics major from Ada, Oklahoma.
I'm Jack Dastugue, a junior finance and accounting student from Dallas, Texas.
I'm Alex Van Noord, petroleum engineering junior from Tulsa, Oklahoma.
I'm Stephanie Vo, a sophomore environmental science major from Oklahoma City, Oklahoma.
And we are Team Ames. Our team leader is Lena Erickson. Our inventors are Dr. Igor Slowing and Dr. Aaron Sadow. And our mentors are Craig Forney and Todd Dorkowski. The increased utilization of cerium is a national priority because this rare earth is mined along with all the other more valuable rare earths. And then it's processed and it's simply stockpiled because it doesn't have enough uses. There's a current 13,000 metric ton overproduction of cerium. The Ames catalyst uses a particular kind of cerium that is the highest surface area ever achieved, which the Ames scientists actually did. This is important because as the surface area of the catalyst increases, its ability for reactivity increases. So let's see how this catalyst would work in a reaction. So it gets with phenol and it activates it to increase the rate of the reaction. So the phenol is hydrogenated into a chemical intermediate called cyclohexanone. Cyclohexanone is turned into a chemical intermediate called caprolactam, which then goes into nylon 6, which is used in carpets, car parts, thread for purses. It's really all around us. Now, this catalyst was disclosed publicly in a scientific magazine in February 2015. This means that it's not an option to internationally patent the catalyst, and it means that there's 1 year to file for a US patent. So our team has given Ames the information it needs to act quickly and decide what's next for this catalyst. Our team has talked to people who have given us industrial, technological, and commercial insights, and we've found 3 key findings. First, we found that there's only one existing company, Honeywell, that Ames could market to. Second, that the catalyst could not fit into current production. And finally, that this catalyst could have value if research could be done so that it could be developed to fit. Now that you know a little bit about how this catalyst came about and a little bit of the background, here's Jack to talk about the market structure.
Thank you, Alexandra. Nylon 6 is a $9 billion industry that will experience 3% long-term demand growth as nylon 6 is rapidly replacing metal applications and industrial products. However, even in this large nylon 6 landscape, there is only one company that is relevant to the Ames catalyst. Before you can get nylon 6, you need the chemical intermediate known as cyclohexanone, and there are 2 production methods for cyclohexanone. The first is the industry-preferred cyclohexane oxidation, which accounts for 90% of cyclohexanone produced in the world. The Ames catalyst cannot fit chemically into cyclohexane oxidation, and therefore cannot access 90% of the market. The Ames catalyst fits into the other production method, phenol hydrogenation, which occupies 10% of cyclohexanone production in the world. This 10% splits down in between 2 companies, Honeywell and Domo. However, Ames has publicly disclosed the catalyst in the United States and therefore cannot file a patent, cannot license to a European company. This means that there is only one reachable company for the Ames catalyst. More importantly, this means that there is only one plant in the entire world that the Ames catalyst can be assimilated into. This is Honeywell's Hopewell, Virginia plant that runs 350,000 metric tons of caprolactam per year. Even then, there are significant barriers that keep the Ames catalyst from being assimilated into Honeywell's Hopewell plant. First off, Honeywell standardly sources its technology internally. We talked to a member of Honeywell's catalyst manufacturing division who told us that it is inherently riskier for Honeywell to externally source its technology because this makes Honeywell lose its financial and strategic control over the research development of the catalyst. Next, Honeywell has very closed-door operations in its nylon 6 segment. We talked to a veteran BASF executive who worked for BASF's nylon 6 production line. He told us that the companies in the nylon 6 industry who have best succeeded over the last 50 years are the companies who have best guarded their intellectual property and have made sure that the secret methods of their production were well hidden. This closed-door dynamic would very greatly inhibit a relationship between Ames and Honeywell. Third, the Ames catalyst does not affect the largest pain point in Honeywell's nylon 6 production value chain. The Ames catalyst works from going from phenol to cyclohexanone. However, the largest pain point in this production chain is going from cyclohexanone to caprolactam in a process called the Beckmann rearrangement. This produces the harmful byproduct ammonium sulfate, which greatly increases Honeywell's regulatory and operational cost. Finally, even if Honeywell was to adapt the catalyst in the face of these 3 previous barriers, they would still need to make large and significant structural changes to their production line. To tell you more about those changes, here's Alex.
Thank you, Jack. Now that the markets have been established, let's take a look into industry operations. There are 2 ways phenol hydrogenation can occur, in liquid phase or in gas phase. Ames developed their catalyst to operate in liquid phase hydrogenation, but it cannot be adopted by the industry in its current state. From our extensive research, we have determined that all the nylon market that uses phenol hydrogenation does so in gas phase. Let's see why. Now, imagine you are a manager at Honeywell. You know that phenol is very expensive, so you, like the rest of the industry, create it in-house. This process is very, very hot, and the phenol that is created is vaporized into a gas. If you were to need this gas in liquid form, it would need to be cooled and compacted with the help of a compressor, increasing energy usage. This liquid is very, very pressurized, sometimes 13 atmospheres of pressure, and it cannot be handled by your typical system, so you would need thick, expensive reactors. Liquid, however, does not flow, nor does it react with catalysts as well as gases do. To keep up with your production rates per year, in Honeywell's case, 350,000 metric tons, you will need bigger reactors. Lastly, catalyst poisoning is a term used in the industry to describe the deactivation of a catalyst over time. Liquid phenol hydrogenation needs to be stirred, but stirring the catalyst with a liquid could damage it, causing it to deactivate very fast. Since your catalyst is dying quickly, it needs to be replaced often, requiring high, frequent, recurring capital costs. As you can see, the industry will not switch over to liquid phase oxidation because of high capital costs and decrease in efficiency. If Ames were to commercialize their cerium-based catalyst, they would have to hit certain goals in development. Currently, Ames's catalyst operates a liquid phase at 35 degrees Celsius with 96% selectivity. Selectivity, in our case, is defined as how pure the produced cyclohexanone is. Cyclohexanone made with Ames cerium catalyst is 96% pure, which is great, but it's not to the same grade made in the industry. Today, the industry operates at 150 degrees Celsius with 99% selectivity. This selectivity is the industrial standard throughout the nylon market and plays into the efficiencies of chemical separators down the production chain. If Ames were to want to commercialize their cerium catalyst, they would have to optimize it for gas phase at 99% selectivity. This selectivity is very high and is very standard throughout the nylon market. Across from this, they would need to optimize their catalyst to operate at 3 degrees below the industrial standard. By operating at lower temperatures, it will lead to a decrease in energy consumption and is the minimum mark that Ames will have to achieve for Honeywell to make an economical investment. Now, here's Stephanie to tell you more about this scale-up process.
Thanks, Lex. The process of scaling up this catalyst would take a significant amount of time and money. This is because the current catalyst has not been researched in gas phase. This means that the researchers at Ames would take an additional 6 months to 3 years to research this catalyst in gas phase and obtain a sufficient amount of information. Only then can it move into the scale-up process. This process takes 3 to 5 years, and this is the point where Ames would reach out to an industry partner, such as Honeywell, and Honeywell would utilize the expertise in their Catalyst Manufacturing Division, UOP, to help scale this catalyst up. Once the catalyst has been thoroughly tested and its performance optimized in the bigger batches, it can be moved into Honeywell's Virginia plant through a swap during its scheduled downtime. We have talked to a technology manager at the UOP Catalyst Manufacturing Research Center who has told us that this process takes a several $million investment, with the bare minimum being $1 million. Taking this into account, if optimized, the Ames catalyst could make a financial improvement to the current commercial process. If we assume the bare minimum $1 million scale-up investment, along with the linear relationship between the temperature and energy consumption, and no requirement for new reactors in its implementation in Honeywell's 350,000 metric ton plant, then Ames brings in $372,000 in yearly operational savings with a break-even in year 3. This is within the typical payback period for this industry, and therefore Ames has the potential to gain the interest of Honeywell and be put into commercial use. Our team recommends that Ames continues to research this catalyst in gas phase and pursue other uses for cerium. If Ames wants to continue to refine this catalyst for the nylon 6 industry, they should be able to meet the minimum optimization requirements that we have set forth. This means the catalyst must be able to perform at gas phase at 147 degrees Celsius and with a selectivity of 99%. If Ames can achieve this, they should approach Honeywell to gauge Honeywell's interest in investment and licensure. If Honeywell is interested, Ames should take steps to patent this catalyst. However, if Ames is unable to achieve the minimum optimization requirements, or if Honeywell is not interested, they should not file a patent. There are still other uses for cerium. The high surface area cerium used in this catalyst is very desirable in many catalytic processes, such as catalytic converters in many of your cars, as well as the breakdown of biomass into biofuels and other chemical feedstocks. Cerium also has uses outside of catalysts, such as in glass polishers and fuel additives to aid combustion. In taking these steps, the Ames National Lab would have the ability to accomplish their goal of utilizing cerium and adding value to this abundant rare earth metal. Our team has evaluated the nylon 6 market. We've analyzed this catalyst's commercial potential and given the Ames National Lab an actionable recommendation for the next steps. With this project, we have been at the nexus of technology and business. Our knowledge has grown about chemistry and the commercialization process. We've bonded as a team, and we've had a metric ton of fun doing it. So we'd like to again thank our mentors, inventors, and the CCEW staff. And we would like to thank you for your time and attention. So we'll now open the floor for questions.